Lesson 2. Changes in state. Reading guide. Key concepts. Essential questions. How is temperature related to particle motion? How are temperature and thermal energy different? What happens to thermal energy when matter changes from one state to another? Vocabulary. Kinetic energy. Temperature. Thermal energy. Vaporization. Evaporation. Condensation. Sublimation. Deposition. Inquiry. Spring thaw? When you look at a snowman, you probably don't think about states of matter. However, water is one of the few substances that you frequently observe in 3 states of matter at Earth's temperatures. What energy changes are involved when matter changes state? Kinetic and potential energy. When snow begins to melt after a snowstorm, all 3 states of water are present. The snow is a solid, the melted snow is a liquid, and the air above the snow and ice contains water vapor, a gas. What causes particles to change state? Kinetic energy. Recall that the particles that make up matter are in constant motion. These particles have kinetic energy, the energy an object has due to its motion. The faster particles move, the more kinetic energy they have. Within a given substance, such as water, particles in the solid state have the least amount of kinetic energy. This is because they only vibrate in place. Particles in the liquid state move faster than particles in the solid state. Therefore, they have more kinetic energy. Particles in the gaseous state move very quickly and have the most kinetic energy of particles of a given substance. Temperature is a measure of the average kinetic energy of all the particles in an object. Within a given substance, a temperature increase means that the particles, on average, are moving at greater speeds, or have a greater average kinetic energy. For example, water molecules at 25 degrees Celsius are generally moving faster and have more kinetic energy than water molecules at 10 degrees Celsius. Key concept. Potential energy. In addition to kinetic energy, particles have potential energy. Potential energy is stored energy due to the interactions between particles or objects. For example, when you pick up a ball and then let it go, the gravitational force between the ball and Earth causes the ball to fall toward Earth. Before you let the ball go, it has potential energy. Potential energy typically increases when objects get farther apart and decreases when they get closer together. The basketball in the top part of figure 8 is farther off the ground than it is in the bottom part of the figure. The farther an object is from Earth's surface, the greater the gravitational potential energy. As the ball gets closer to the ground, the potential energy decreases. You can think of the potential energy of particles in a similar way. The chemical potential energy is due to the position of the particles relative to other particles. The chemical potential energy of particles increases and decreases as the distances between particles increases or decreases. The particles in the top part of figure 8 are farther apart than the particles in the bottom part. The particles that are farther apart have greater chemical potential energy. Thermal energy. Thermal energy is the total potential and kinetic energies of an object. You can change an object's state of matter by adding or removing thermal energy. When you add thermal energy to an object, the particles either move faster, increased kinetic energy, or get farther apart, increased potential energy, or both. The opposite is true when you remove thermal energy from an object. If enough thermal energy is added or removed, a change of state can occur. Key concept check. How do thermal energy and temperature differ? Solid to liquid or liquid to solid. When you drink a beverage from an aluminum can, do you recycle the can? Aluminum recycling is one example of a process that involves changing matter from one state to another by adding or removing thermal energy. Melting. The first part of the recycling process involves melting aluminum cans. To change matter from a solid to a liquid, thermal energy must be added. The graph in Figure 9 shows the relationship between increasing temperature and increasing thermal energy. Potential energy plus kinetic energy. At first, both the thermal energy and the temperature increase. The temperature stops increasing when it reaches the melting point of the matter, the temperature at which the solid state changes to the liquid state. As aluminum changes from solid to liquid, the temperature does not change. However, energy changes still occur. Reading check. What is added to matter to change it from a solid to a liquid? Energy changes. What happens when a solid reaches its melting point? Notice the line on the graph is horizontal. This means that the temperature, or average kinetic energy, stops increasing. However, the amount of thermal energy continues to increase. How is this possible? Once a solid reaches its melting point, the average speed of particles does not change, but the distance between the particles does change. The particles move farther apart and potential energy increases. Once a solid completely melts, the addition of thermal energy will cause the kinetic energy of the particles to increase again, as shown by a temperature increase. Freezing. After the aluminum melts, it is poured into molds to cool. As the aluminum cools, thermal energy leaves it. Freezing is a process that is the reverse of melting. The temperature at which matter changes from the liquid state to the solid state is its freezing point. To observe the temperature and thermal energy changes that occur to hot aluminum blocks, move from right to left on the graph in Figure 9. Liquid to gas or gas to liquid. When you heat water, do you ever notice how bubbles begin to form at the bottom and rise to the surface? The bubbles contain water vapor, a gas. The change in state of a liquid into a gas is vaporization. Figure 10 shows two types of vaporization: evaporation and boiling. Boiling. Vaporization that occurs within a liquid is called boiling. The temperature at which boiling occurs in a liquid is called its boiling point. In Figure 11, notice the energy changes that occur during this process. The kinetic energy of particles increases until the liquid reaches its boiling point. At the boiling point, the potential energy of particles begins increasing. The particles move farther apart until the attractive forces no longer hold them together. At this point, the liquid changes to a gas. When boiling ends, if thermal energy continues to be added, the kinetic energy of the gas particles begins to increase again. Therefore, the temperature begins to increase again, as shown on the graph. Evaporation. Unlike boiling, evaporation is vaporization that occurs only at the surface of a liquid. Liquid in an open container will vaporize or change to a gas over time due to evaporation. Condensation. Boiling and evaporation are processes that change a liquid to a gas. A reverse process also occurs. When a gas loses enough thermal energy, the gas changes to a liquid, or condenses. The change of state from a gas to a liquid is called condensation. Overnight, water vapor often condenses on blades of grass, forming dew. Solid to gas, or gas to solid. Is it possible for a solid to become a gas without turning to a liquid first? Yes, in fact, dry ice does. Dry ice, as shown in Figure 12, is solid carbon dioxide. It turns immediately into a gas when thermal energy is added to it. The process is called sublimation. Sublimation is the change of state from a solid to a gas without going through the liquid state. As dry ice sublimes, it cools and condenses the water vapor in the surrounding air, creating a thick fog. The opposite of sublimation is deposition. Deposition is the change of state of a gas to a solid without going through the liquid state. For deposition to occur, thermal energy has to be removed from the gas. You might see deposition in autumn when you wake up and there is frost on the grass. As water vapor loses thermal energy, it changes into a solid known as frost. Reading check. Why are sublimation and deposition unusual changes of state? States of water. Water is the only substance that exists naturally as a solid, a liquid, and a gas within Earth's temperature range. To better understand the energy changes during a change in state, it is helpful to study the heating curve of water, as shown in Figure 13. Adding thermal energy. Suppose you place a beaker of ice on a hot plate. The hot plate transfers thermal energy to the beaker and then to the ice. The temperature of the ice increases. Recall that this means the average kinetic energy of the water molecules increases. At 0 degrees Celsius, the melting point of water, the water molecules vibrate so rapidly that they begin to move out of their places. At this point, added thermal energy only increases the distance between particles and decreases attractive forces. Melting occurs. Once melting is complete, the average kinetic energy of the particles, temperature, begins to increase again as more thermal energy is added. When water reaches 100 degrees Celsius, the boiling point, liquid water, begins to change to water vapor. Again, kinetic energy is constant as vaporization occurs. When the change of state is complete, the kinetic energy of molecules increases once more, and so does the temperature. Key concept check. Describe the changes in thermal energy as water goes from a solid to a liquid. Conservation of mass and energy. The diagram in Figure 14 illustrates the energy changes that occur as thermal energy is added or removed from matter. Notice that opposite processes, melting and freezing, and vaporization and condensation, are shown. When matter changes state, matter and energy are always conserved. When water vaporizes, it appears to disappear. If the invisible gas is captured and its mass added to the remaining mass of the liquid, you would see that matter is conserved. This is also true for energy. Surrounding matter, such as air, often absorbs thermal energy. If you measured all the thermal energy, you would find that energy is conserved.